All right, this is Honors Algebra 2 Pre-Calc. We are doing 4.2 in Algebra 2, which is matrix multiplication. So this particular video, which is the second in the series on this section, is going to focus a little bit on the applications that your book lists. So we're going to walk through an E2P2 and an E3P3, all of which are going to be applications, and then after that we'll have a separate video where we do some extra stuff. Okay, so Carl and Kayla are making two snack mixes by mixing dried fruit and nuts. The amount of protein, carbs, and fat in grams per serving for the dried fruit and nuts are given in Table 1. The number of servings of dried fruit and nuts for each mix are given in Table 2. Represent the information in Table 1 in a matrix called N, represent the Table 2 in a matrix called G, and then find NG to determine which mix has more protein and less fat. Okay, so the thing to notice here is when you do a word problem like this, it's not an accident that this set's columns and this set's rows have the same contents. Like this is the same stuff, right? And that's not an accident, because what's going to happen is those are our inner dimensions, right? So those are our inner dimensions and they're the same. Not only are the dimensions the same, but they are actually the same numerical values. If you look back to the very beginning of this thing when we talked about the football problem, that's true there too. In that football problem, the columns of the first matrix represented touchdowns, extra points, and field goals, and then the rows in the second matrix were touchdowns, extra points, and field goals. So it's not an accident that they're the same, and that our outer dimensions, which are going to be these guys, are going to end up staying the same. So what's going to happen is that when we multiply these matrices, we're going to end up with a matrix that is protein, carbs, and fat as the rows, and sports mix and camp mix as the columns. So let's go ahead and do the first thing they ask. The first thing they ask is for us to make a matrix N where they literally we just write these 6 numbers, right? So we're going to write these 6 values in order. So N is going to be 3, 20, 65, 21, 1, and 52. And my G is going to be 4, 3, 2, and 3. And they want us to multiply the two of them together. So NG is going to look like this, right? It's going to be 3, 65 rather, 21, 152 times a 4, 3, 2, 3. Notice that this is a 3 by 2 times a 2 by 2. The inner dimensions match. So what's going to happen is our answer is going to be a 3 by 2, right? But not only is it going to be a 3 by 2, which is going to look like this, right, if we do that, but it's going to be a 3 by 2 where this is proteins, carbs, and fat, and this is the sports mix, and this is the camp mix, right? So our final answer is going to give me those pieces of information to tell me about protein, fat, and carbohydrates in each mix. So let's go ahead and walk through this. So we're going to take row 1 and column 1. 3 times 4 is 12. 20 times 2 is 40. So we're going to get 12 plus 40, which is definitely a 52. And I didn't really give myself enough room to make myself an answer matrix, but we're going to try and make it happen, right? We're going to squeeze this 52 in here into my answer matrix that's totally just barely going to squeeze these numbers in. Okay, and that's going to be protein, carbs, and fat, sports mix, camp mix. All right, cool. Row 1, column 2 is going to be 3 times 3, which is 9, plus 3 times 20, which is 60, so that's going to be 69. Row 2, column 1 is going to be a lot of fun. 65 times 4 should be 130 times 2. So there should be a 260, right, and a 42. So we should get 302. This might be one where you cave and use a calculator. 65, 21, and the 3 and 3 is going to be 180 and 15. So that's a 195. Right, and 3 times 21 should be a 63, right? So it's 5 shy of being a 263, so it's a 258. Cool. All right. Again, you can double check me on this because my mental math is not always the best. Last row, first column, 1 times 4 is a 4. 52 times 2 should be a 104, so this should be 108. Right? And then last row, second column, 1 times 3 should be a 3, right? And then 3 times 52 should be a 156. So this should be a 159. Okay, so there's my answer matrix, and then we're supposed to use that matrix to answer some questions. In order to do that, I'm going to erase to get myself a little bit of space. So if I erase to get a little bit of space, what I'm going to see is that what they're asking is which mix has more protein and which has less fat. Okay, well, protein is the middle thing, right? Or sorry, is the top row. My bad, protein's the top row, right? So more protein is going to be the camp mix, right? So the camp mix has more protein. So more protein is the camp mix, right? Because 69 is greater than 52, right? And less fat, well, less fat is going to be the sports mix because 108 is smaller than 159. So less fat is the sports mix, right? Because 108 is smaller than 159. Okay? Cool. All right, moving on. So same idea, right? But we're gonna tack on one more mix here. We're gonna tack on a mix. Let's see, trail mix. So we're gonna make an extra thing. We're gonna call this trail mix. I'll just call it T. It has 2 servings of fruit and 4 servings of nuts. Okay, and they ask what are the entries in the new matrix G, right? So my new matrix G is going to be 4, 3, 2, 2, 3, 4, right? And we already saw my N from before was this matrix right here. They ask us to find the new NG and say which of these 3 mixes now has the greatest amount of protein, which one has the greatest amount of carbohydrates. So I'm going to be honest here and tell you that I'm going to cheat just a little bit. So if we do N times G, right, it's going to be the 3, 20, 65, 21, 1, and 52. Right, times this new matrix that's 4, 3, 2, 2, 3, 4, right? So this is a 3 by 2, and this is a 2 by 3. So my answer is going to end up being a 3 by 3. But here's the thing I want to show you. It's not a 3 by 3 where we actually have to generate the answers from scratch. Okay, so in a second, okay, so this is definitely a 3 by 3. The inners are the same. My answer is 3 by 3. But remember, this was protein, and this was carbs, and this was fat, and this was the sports mix, camp mix, and trail mix. Okay, so I'm going to be kind of a lazy bum for a sec, right? I'm going to go back for a sec to my answer, and I'm going to screenshot this because I kind of want to be lazy. I already know how much is in these. I know that this is a 52, a 69, a 302, a 258, a 108, and a 159. Those didn't change, right? Because the only difference is that this column didn't exist in the original. So the only difference here is that I'm not going to reinvent the wheel. I'm not going to re-find these 2. I'm going to recognize that, oh, hey, I tacked a column onto the end. So now I do this row times this column. I'm going to get 6 and 80. So 6 plus 80. So the new column, right, this is going to be 6 plus 80, which is going to be an 86. If I take... So that was if I take this guy in green, right? If we do second row, that same last column, I'm going to get a 130 and an 84. So that's a 214. And if I do last row, that last column, I'm going to get a 2 and a 208. So that should be a 210, right? So the point I'm making is that it's not cheating if sometimes when you're doing a problem, you notice that you can use your own work in a smart way. And you could even say that, like if you were, I wouldn't give this to you on a test, but if I did give it to you on a test in this way, you could be like, hey, Hogan, I'm not silly. This part of the matrix was definitely the answer from E2. And that's not wrong because it would be the same. And you might not even spot that right away, but as you started to fill it out, the numbers might start to look familiar and you might think, wait a second, I'm not going to do that. So the question we're asked is which mix has the greatest amount of protein? Well, so for the greatest amount of protein, right, we can see now that we have the trail mix. We want to go with the trail mix, right? Because the protein is the top row and the trail mix definitely has the most protein. Which of the mixes has the greatest amount of carbs? Well, the greatest amount of carbs would be the sports mix, right? So sports would be the greatest amount of carbs. And I wrote that backwards, but instead of before I wrote protein and then trail. But those are the answers to the 2 questions that they asked. All right, cool. Let's talk about another application. So a network is a finite set of connected points. Each point is called a vertex. The plural of vertex is vertices. We talked about that in the first video about matrix and matrices, right? A directed network is a network in which permissible directions of travel between the vertices are indicated, right? So like here, if you wanted to go from K to L and from L to K, you could because there's arrow in both directions. But if you wanted to go from J to K, you could, but not from K to J, right? You can represent a network in an adjacency matrix, which indicates how many one stage, as in direct, from one to the other paths are possible from one vertex to another. A directed network and corresponding adjacency matrix are shown below. So let's just walk through how this matrix happened, okay? So from J to J, well, if you're at J, you can't move back to J in one step, so there's no ways to do it. From J to K, well, there's one way to get from J to K, right? This is the one way to get from J to K. And from J to L, there is no way to get from J to L in one step because you're not allowed to go this way. The arrow says you're not allowed, so that's why that's 0. To get from K to J, well, you can't go from K to J in one step because that arrow says you can't travel that way. To K, the same thing. There's no way to get back to K from K. K to L, there are two ways, though. You could either go this direction, that gets you to L, or you could go this direction, which is why this is a 2, right? Now L, there's a bunch of different things we can do. L to J, because this arrow goes directly in this way to J, is one way. L to K, you can go two different ways. You can either go across the middle, or you can go down this bottom route. And then L to L, there's actually a loop. You can start at L and loop back to L, right? So that's why this looks the way it looks. So with the points traveled from naming the rows, so the points traveled from naming the rows, the points traveled to naming the columns, the matrix shows that there is no path from J to itself, right? That's what A11 says. But there is a path from L to itself. That's what A33 says. And there are two paths between from K to L, and from L to K. So if A is the adjacency matrix of a network, then the product A times A gives the number of two stage paths from one vertex to another vertex by means of one intermediate vertex. For instance, L to K by means of J. So if we, let's walk through how that works. And it's actually cool. Networks are really interesting. So computer networks work this way, right? But so do lots of interesting, complicated math problems. It's pretty cool. So let's go ahead and walk through this. All right. So we're going to go ahead and refer to the directed network that we have from the last thing, and we're going to go ahead and find a matrix that gives the number of two stage paths. Now, we can either do this by multiplying by hand, or honestly, you could just go ahead and put these in a calculator, right? So one option is to go to my matrix. So I'm going to go to second matrix, right? I'm going to go to edit. I'm going to pick A, and I want to make A 3 by 3 matrix. So it's 0, 1, 0, 0, 0, 2, 1, 2, 1, right? So double check that it's right before you quit out, and then quit out. And so then what I can do is I can go to second matrix, and I can pick A, and I can either do A times A or I can do A squared. Either one will give me the same answer, and this is what I'm going to get. So now I'm going to pull this away, and I'm going to walk you through. So what I'm going to do is pull this away and walk you through that. That's exactly what they did with their with the calculator. Okay, so basically, if I want to know, if I want to interpret A32, right? So if we go to interpret A32, right, which is right here, right? We know that that means from L to K. So there are 3 ways to get to K using 2 paths, right, from L. So here are those 3 paths, right? So I could do L, right? So start at L, go back to L, and then go to K, right? So L to L, going to K. I could do the same thing another way by doing start at L, go back to L, go this path to K. Or I could have done L to J to K, which is that. So walk through P3. So we're going to go ahead and start with making a matrix that represents the directed network for this picture right here, right? So we're doing an adjacency matrix. So remember that we have the from, so from X, Y, and Z, and then up here we have the to X, Y, and Z. All right, so from X to X, there is one path, because you can start at X and follow the loop around and land back at X, right? From X to Y, there is one path, there's this path. And from X to Z, there's this path, because you can't take the other one because it has the wrong directional arrows. There's only one. Okay, so from Y to X, there's this path, that's 1. from y to y there are no paths because there's no loop back to y, and from y to z there's this one path. Z to x there are two paths. I can either go this way or I can go all the way around the loop, right? So there's two paths. Z to y is just this one path in the middle, right? And there are no loops from z to z. Cool. So that's what I'm going to put in as my matrix A in my calculator, right? So if I bring my calculator over here, I go to second x inverse, and I'm going to go to matrix A, and I'm going to show you that I actually already have that in my calculator, right? So I have my matrix M in the calculator right there. All right, so then I'm going to quit out, right? And actually we can put this here so we can see both. And I'm supposed to do M squared, which again for our purposes will be matrix A, right? Because I don't bother to go all the way down to M. So I'm going to do A squared and hit enter. And so this is the matrix that I'm going to get when I do my M squared. So we're going to take a quick screenshot so we can drag that on and not have to do a bunch of stuff with it. Okay, cool. So let's, so this was my part A, right? Well, so this is actually before part A. Part A was what's my M squared, right? And that's right there, right? And then part B says look at entry 2, 2. So that's row 2, column 2, which is here, right? So that would be y to y, right? Because this is from x, y, and z, and this is 2x, y, and z. So that would be y to y in 2 stages, right? So 2 stages. And full disclosure, the reason that this video is slightly disjointed from the last one is because I did this whole problem, and then I had to do the part where they asked me to list the corresponding paths, and my brain just completely blanked, right? So the reason my brain blanked is because every time I looked at it, the only way to get back to y involved 3 steps. Well, that's because I kind of neglected to notice the double directional arrows. So the first path option would be y to z and then loop right back to y on the same path, right? Because that's a double directional path. So path number 1 would be y goes to z, and then you take the exact same route back to y. It's like you forgot your keys, right? And then the other path to get to y, if we erase that green mess that I have, the other path to get to y, which we'll do in blue, is go to x and then go right back to y, like you forgot your keys again. So again, y to x to y, and those are the only 2 ways to go from y to y. Again, my brain totally blanked on that when I was doing this the first time, and that's entirely why we have this second part of the video that's a little disjoint, is because I just totally blanked. So there we have it. Again, that's kind of a cool thing. It's got lots of applications for when you talk about like traffic, both in the real world traffic, but also like lots of things are described by directional and directed networks, right? So lots of things can only move in one direction, or in some cases can move in both directions, and it's kind of cool. So there you have it.